Hey there, chemistry students. Welcome to our fourth and final time talking about the gas laws. We're going to look specifically at non-ideal gases. So all unit long, we've been talking about ideal gases and ideal gas behavior and these gas laws and how we can predict reasonably well the behavior of gases. Well, what happens if they don't follow the rules that we have made for them? Because they're kind of our rules after all. Well, we're going to look at that today. The good news is it's very predictable when and how they will differ from ideal gases. And that's probably why it's so often on the AP exam. Okay, I was trying to get to the next screen. Okay, so let's start at the beginning. For gases to be ideal, we as chemists have to make two very, very, very big assumptions. We are going to assume there's no intermolecular attractions. So as they're roaming around, this particle here is not attracting this particle here, okay? And that's usually a pretty safe assumption as they're pretty far apart. Like magnets, the farther apart you get them, the weaker they pull on each other, right? Coulomb's law again. Distance, inverse square of the distance. We also assume the volume of the particles of gas is zero. Now this works pretty well because gas particles are itty bitty teeny tiny. Like you really truly could not imagine how tiny a gas particle is. So is that worth zero? Well, no. It's not officially zero is the problem. So we're going to get to that in a minute. So when these assumptions fail, or we say the gas is a non-ideal gas or behaves less than ideally, or some vocabulary like that, that's when we need to consider these topics. So we're going to focus our attention on these two assumptions and when do these assumptions fail. First thing that would cause them to fail is when there are intermolecular forces. I mean, we know in truth there are intermolecular forces in gases. Gases that can do hydrogen bonding tend to fail a lot more often. They tend to be much less than ideal. There's going to be an attractive force between the particles. And what's the consequence? The pressure will be less because they're being pulled closer to each other. They're not hitting the walls of the container as often or as hard. Gases that are polar, even though they can't do hydrogen bonding, are going to be a little less than ideal. And then gases that have a lot of electrons, like big gas molecules, lots of electrons roaming around. I mean, one of the famous ones for London dispersion forces is iodine. Well, iodine's not a gas at room temperature. Okay, it pulls itself together too much. But a very heavy gas like radon, lots of mass and lots of electrons. So it's going to behave less ideally than, say, helium. Helium does not have many electrons, so it's going to have very weak IMFs, very weak London dispersion forces. So what's the consequences when they are pulling them together? Well, this makes sense. If they're pulling each other together, they have less pressure because they're not hitting the walls as often, and they're not hitting the walls as hard because they're pulling each other together. Okay, so the pressure is going to decrease if there's a lot of intermolecular forces. It's going to be, the pressure will be less than expected by the ideal gas law or something like that. That's how they would phrase it. Okay. Here's another way. Okay, do the IMFs cause it to deviate because we're getting the particles closer together? Okay, so again, ways that this could happen is we increase the pressure. So look at my before and my after. Before, I have just a few molecules in that container, right? They're pretty far from each other. Now I've added a lot more molecules to that container. They've got to be a lot closer to each other. If they are a lot closer to each other, because I've increased the pressure by increasing the amount of particles, then they're going to be able to attract each other better and stronger, and they will exhibit less than ideal behavior. It would, even though, like, say, I would expect, I don't know, if this is a pressure of 1 atmosphere and this is a pressure of 10, I would think in real life, I wouldn't hit a pressure of 10 atmospheres. I'd hit a pressure of like 9.9. They're pulling themselves together more, not hitting the walls as hard. For the same amount of molecules, the pressure is going to be less than we would predict with the ideal gas law. Another way to get them closer to each other is by decreasing the volume. Now here I have the same number of particles, 7 over here, 7 over here, but obviously in the smaller container, they're got to be closer to each other. So I would expect, let's say this smaller container is half the size, I'd expect the pressure to double. Well, it's not exactly going to double. Because they're now close enough, they can pull each other together, pressure might be 1.97 times bigger and not 2 times bigger. Okay, you see how the pressure is going to decrease because of those intermolecular forces pulling it together. And then temperature. I expect temperature to have an effect, okay? And this is not something I could draw. This is something to write. Oop, that didn't work. Let's go back. It helps if I have a pen ready. Ooh, bright pink. I'll do bright pink. Okay, so decreasing temperature. What's that going to do? Okay, well, there's a progression here. Decrease temperature means decreased average kinetic energy. Wow, that's a K. Average kinetic energy, which means decreased velocity. If they're moving around less quickly, now they're able to notice each other's there. So therefore, it's going to decrease the pressure, because even though I would think, oh, we'll cool it down to like 100 kelvins and the pressure should be this. Well, it's going to be a little less than that, because now you've cooled them down, they've slowed down on average, and those intermolecular forces can pull them together. They're hitting the walls of the container less often and with less force, and so the pressure is going to be less than I expect it to be. So there we go. So we get less ideal behavior if we have high pressures, very small volumes, and very low temperatures. But we're not done yet. Let's keep going. Maybe. Oh, I have to close the little drawing box first. You know, and I should have cleared the drawings first. Well, I'll get it figured out one of these days. Here we go. Okay. You know, we also said it's not just those intermolecular forces that could cause it to deviate from ideal gas behavior. It could also be because of the size, the physical amount of space the molecules take up. So when is it going to be noticeable? When is it going to be less than ideal behavior that we're going to take up more space? Well, increasing pressure is one of those. Now check this out. In my before I have 5, and my after I have a lot, 20 maybe, something like that. What do I expect to happen? I expect the volume to actually be bigger than ideal gas law would tell me. Because now, not only are they moving around, taking up the space, they're hitting each other, they're noticing each other. So the volume is actually larger. You have to account for that extra space taken up by so many particles. So increasing pressure makes it deviate from ideal gas law behavior, because now the volume is going to be a little larger than we predicted. Okay? And then decreasing volume, now that's going to be interesting, okay? Decreasing volume, you can see, okay, you can see what happens here. Now I want to go to an extreme, but I want to draw this extreme, and you have to, okay, pretend I'm a good drawer. Okay. Let's say I squish it. Can I make the volume completely 0? If it was a perfect ideal gas with 0 volume for the molecules, yes, I would be able to make the volume of my box 0, but I can't do that. In reality, this is supposed to be a box, a very small box. In reality, at some point in time, I squeeze it so much that I have all those gas particles just lined up flat on the bottom, and I can't squish it anymore. I could never truly get a volume 0 because those gas particles do take up some amount of space, and by taking up some amount of space, it prevents me from hitting a true 0 mark. So if ideal gas law was true, I could hit a volume of 0. But gases do not always behave ideally, and so I can't truly hit a volume of 0. The volume will always be a little larger than the math makes it out to be. So have you noticed the different effects? The effect of pressure. Pressure is less than the formulas would tell us it should be. Volume is going to be greater than the formulas tell us it's going to be. And do you know why now? Can you understand it? Because I don't want you to memorize non-ideal gases have a larger volume and a smaller pressure than ideal gases. I want you to memorize that. I want you to know it and understand it and be able to explain. They could ask you that, be able to explain your reasoning as to why it's going to be that way. Very often on the test, they would give you a question of, this gas does this, like less volume or less pressure than predicted. Explain why. And you say, well, because of the intermolecular forces pulling the molecules together, they hit the walls less often and with less force, and therefore the pressure is less than ideal. It rolls off my tongue well because I understand it, and that's what I want for you. I want you to understand it, not memorize it. I want you to understand. Makes sense. If the things are being pulled together, the pressure, which we measure the walls of the container, the pressure is less. If the volume for the particles are there and I'm squishing, there's a point where the volume is not going to be as low as I can get. Okay, the volume is going to stop. So the volume's larger than the possibility of a 0 volume. So that's what are the conditions, and that is what happens because of this. Let's summarize. Okay. Oh, I didn't clear. What are the conditions where I am likely to have a gas deviate from ideal gas behavior? What do we know about pressure? I'm less likely to get ideal gas behavior if my pressure is, did you say large? If my pressure is large or high. At high pressures, I'm less likely to get ideal gas behavior. So actually, I'm sorry, I'm writing this wrong on the screen. I want to actually write what is best to get ideal gas behavior. If high pressures make it deviate, then I want low pressures to make it best, like, I don't know, 0.1 atmospheres is a good low pressure. Down around 100 millimeters of mercury, that's a good low pressure. Okay, much lower than standard pressure. All right, so the lower the pressure is, the more likely it will be ideal. Do you see how I'm saying that? Because I got myself confused a moment ago. I'm sorry for offering that confusion. Temperature, what is likely to keep it acting ideally? Well, if low temperatures made it not act ideally, then I want, now watch how I'm going to say this. I'm going to get a different color to set this off. Let's do this. Okay. I'm going to say this average to high temperatures. Okay, and I say that because I want you to understand 273.15, which is 0 degrees Celsius, that is already pretty high for gases. That's high enough that they're going to act pretty much ideally due to the temperature anyway. So I wanted you to think normal temperatures are ideal, because they are. So I don't need to get much higher. Yeah, you know, 600 kelvins. absolutely going to help make it ideal. I don't need 3,000 kelvins before it becomes ideal. That's what I want you to understand. In fact, if you go too high, you run into other issues because you're, turning atoms into plasma and stuff like that. You don't want to do that either. Okay. Normal temperatures, like in the classroom, are already warm enough to be ideal. Even slightly warmer than classroom, warm enough to be ideal. You don't need to get super duper, ooper schmooper hot in order for it to be ideal. What we want to avoid is very low temperatures. Let's avoid 50 kelvins. That would be less, that would deviate from ideal behavior. Even 100 Kelvin, now I'd be like, you're kind of in the iffy zone. I'm not comfortable with that. Too low to really be comfortable expecting ideal behavior. Almost 300, yeah, that's fine. We're likely going to experience ideal behavior. 600, sure, likely to experience ideal behavior. I don't need 3,000 or 1,000 even, something like that. Okay, so what are they going to ask you on the test? These come up all the time on the test. What do they expect you to know? If the intermolecular forces are greater, like it can do hydrogen bonding or dipole-dipole, then it's more likely to deviate from ideal gas behavior. It's more likely not to behave like an ideal gas. If the pressure is high, it's more likely to deviate, so low pressures help keep them ideal. If it's low temperature, it's more likely to deviate, so higher average room temperature and higher tends to help make it ideal. Okay, know those conditions, know why, for the same reasons we literally just discussed, and then that's all you need to know about non-ideal gases. That's the sorts of things they expect you to know for the test. Okay, so I wish you luck on our review. Why is this not? Okay. Anyway, wish you luck on our review, and I will see you next time.